Today, I'd like to talk to you about a paper I did during my PhD, where we explored the idea of making a gravitational wave time and array with LISA. I'm currently a postdoc at the University of California in Santa Cruz. This project was done in collaboration with, at the time, colleagues from the Southern Methodist University at Dallas, Joel Myers, Noah Pearson, and Cynthia Trendafilova, and my PhD advisor in UT Austin, Aaron Zimmerman. Here's the archive number if anybody wants to take a closer look. Now I'll tell you a little bit more about the motivation for this project and the big overview. So one day, Joel Myers, a good friend of Aaron, my advisor, asks, want to use the LISA white dwarf binaries as clocks for lower frequency gravitational waves, just like PTAs do with pulsars, trying to detect the gravitational waves from supermassive black hole binaries. So Aaron was like, interesting, gravitational waves detecting gravitational waves, but I don't know, it might not be the strongest signal and the loudest carrier for doing this, but I mean, Joel did have a point, it's LISA, so we'll have a continuous cadence for like 4 to 10 years. There's going to be tens of thousands of sources, unlike PTAs, now at least. And then there's no plasma dispersion effects or radio interference to screw with you. But yeah, I mean, on the other end, it's intrinsically weak signal, and there's also not as accurate as a clock as a pulsar, a white dwarf binary. So as an overview, first, I'd like to tell you about the signal as it would affect an individual binary, both in the time and frequency domains. And as it turns out, the frequency domain is particularly useful in keeping an intuitive picture of the effect of the different variables that affect the signal. So we'll keep that in mind for later. And second, I'd like to tell you about the sensitivity of an array of binaries and how it scales as a function of the different parameters. Okay, so main idea behind this project is you have a high frequency gravitational wave like this one's propagating in a space-time that is imbued with a low frequency gravitational wave, just as the one's cartoon there. And the idea is that this high frequency gravitational waves will carry information about that background wave. So specifically, if this is the background modulating wave up here in the top to right, what we figured out is that the carrier wave would have this sinusoidal oscillation in its frequency as a function of time. So another way to think about it is that the peaks and valleys of the wave will arrive at different times, and one could measure these times to get the background wave. Hence the name, which actually originate from the ideas behind pulsar timing arrays, which are very similar. So more quantitatively, the strain that we would measure from a gravitational wave is the one like what we would measure from a gravitational wave is the strain, right? And the strain is, as you well know, the compression expansion of space as a function of time. So without the background wave, for each given carrier source dubbed here with a subscript I, we have a simple monochromatic carrier wave with amplitude, frequency, and phase. The modulating wave adds this extra sinusoidal modulation, which, as you can see here, is specific to each carrier because of all of the ith parameters, like fi and so on, gamma I. So perhaps I want to dive a little bit into parameters, but the best way to do that perhaps is in terms of an example of what we could actually measure. So up in the corner is a potential source of the gravitational waves, a supermassive black hole binary. As the black holes spiral into each other, they release gravitational waves with a certain frequency Fm, an amplitude Am, and a phase alpha M. The waves propagate across the universe, and they eventually reach a source of high-frequency gravitational waves, say a white dwarf binary in the Milky Way, as a dim plane monochromatic plane wave propagating with some direction k hat. Now, one can summarize the metric perturbation effects due to the binary black holes to those related to the metric perturbation at the white dwarf binary and the metric perturbation on Earth. The rest are expansions and contractions with the same amplitude that cancel each other out. So a way to envision this metric perturbations is like the rocking of the white dwarf and the Earth as the modulating wave passes. So it would be the relative motion of the two that matters for the overall modulation. The amplitude of such modulation of the white dwarf's frequency is directly proportional to the amplitude of the background wave AM, and is inversely proportional to its frequency, as you can see here. The modulation is also different for each binary. It is directly proportional to their frequency, Fi, and it depends on the distance that they have to propagate across to reach Earth, DI, as well as their location relative to the black hole wave, Fi, their geometric factor. Okay, so a better space to understand this modulation, I think, is for Fourier space. In Fourier space, monochromatic waves should, given infinite time, just appear as delta functions. But if we observe a monochromatic wave for some given time t, the delta function will actually become wider and shorter, just like the one in the picture. And this is a representation of what our signal would look like. And as you can see, one will have a main peak due to the carrier wave, and two symmetric sideband peaks due to the modulating wave. The longer we observe, the higher and thinner all peaks get. The central peak is located at the frequency of the white dwarf binary, and the sideband peaks are at plus and minus the black hole binary frequency. It is important. This is very important because the displacement will be the same for all white dwarf binaries that are affected by this background wave. So all of them all across the galaxy. But unlike the placement, the amplitude will vary for every white dwarf binary by their individual geometric factor and their own frequency and whatnot. Now, a further complication comes from the fact that the black hole binary may evolve into a higher frequency over the time that the white dwarf wave takes to propagate all the way to Earth. So there's actually two extreme cases: either the evolution is negligible, or the contribution from the metric near the white dwarf adds to the Earth's one, or it's so fast that the contributions are separate and appear as two different pairs of sideband peaks, as you can see to the right. So in this paper, as a first pass, we decided to concentrate in these two extremes and not actually treat the in-between. Okay, so far that was the signal, but most of the hard part of this paper was actually calculating the sensitivity to the modulating black hole binary wave. And we tried 3 different approaches. We tried timing, match filtering, and Fisher analysis. And the timing estimate is more akin to what people in the literature do for timing arrays, and measures the time differences in the peaks between what is expected without a modulating wave and what you have, and it gives the correct crude overall shape. But then we did match filtering, which gave us a correct high frequency limit, but it didn't take into account the uncertainties of the estimated parameters of the white dwarf binaries and the black hole wave itself, which are really important at the low frequency limit when the sidebands start to overlap with the carrier. So finally, we just did a full-fledged Fisher analysis and properly modeled the sensitivity at low frequencies. So sure, here is the outcome of that full-fledged Fisher analysis using the whole array, not just one, as I showed you before. And the main things to concentrate on are the shape and scaling. This plot is dimensionless variables to show the shape of the sensitivity. The way to think about this plot is the right side of the sensitivity corresponds to the case where the sideband peaks are distinguishable from the central peak, because of the frequency of the background wave or the integration time, making it slimmer. The left is where they are merged with the central peak. In the high frequency limit, most uncertainties are actually irrelevant, but the low frequency limit can actually have significant differences depending on the unknown parameters, like the phase and polarization of the background wave, as shown in these 2 solid curves. So overall, the first order, this dimensionless curve can be scaled by the signal to noise of the sideband peaks, which are directly proportional to the amplitude of the modulating wave and inversely proportional to its frequency, as well as the squared sum of the signal to noise, frequency, and geometric factor of all of the monitored gravitation, monitored white dwarfs. So in general, the more white, you know, a lot of words, but in general, the more white dwarfs, the better, but it also depends on their location and frequency, similar to PTAs, of course. So once we had the shape and scaling, we decided to take a mock galaxy and a mock Lisa reduction pipeline, which were readily available online. And out of the around 10 million white dwarfs in the Milky Way, there are about 10,000 white dwarfs in LISA that LISA will be able to detect with at least a signal to noise of 7. And they're readily available pipelines and datasets in Milky Way datasets. So we used a galaxy from the LISA data challenges and the G.V. Fisher code written by Tyson Littenberg. And using those, we estimated the sensitivity that LISA would have to distance for massive black hole binaries. I'm going to skip this. Okay. So finally, here are different sensitivity estimates compared to the PTA. The timing curve is done essentially applying the PTA method to our setup and doesn't consider all the systematics we took into account in the Fisher analysis. And the solid curve corresponds to the Fisher analysis in the different limits discussed earlier. As you can see, well, at the end, we do much worse than videos where we overlap. We do have a range of frequencies we'd be uniquely sensitive to. So, conclusions. Hey, I mean, it's pretty cool. Gravitational waves. You can use gravitational waves to detect gravitational waves. LISA will have some sensitivity to gravitational waves in the microhertz regime at zero cost. This is also the first, as far as we know, frequency domain analysis and analytical sensitivity estimate of time arrays. And it's extendable to PTAs or gravitational wave detector sources and carriers. Thank you so much. And that would be it.